good. Okay, now we have Stefan talking about parallelism and scheduling fairness.
Thanks. So this is joint work with Sam Westrick and Amudachar, who I think are both here, so feel free to ask them questions as well. So let's begin by supposing that I'm a robot, and I want to find my way from my office at Carnegie Mellon to the Pittsburgh airport so I can come to ICFP. So I can begin by finding my route from Carnegie Mellon to the airport, which roads to take and so on, using an interface that looks suspiciously like Google Maps. But before I can get there, I need to solve a very different problem, which is getting out of my very cluttered office. Now, these are really two separate problems, navigating which roads to take and navigating around furniture, people, and other obstacles. And roboticists actually use different algorithms to solve them. So we might actually want to run these two different kinds of algorithms simultaneously in the same system, but they have two different priorities because they're sort of planning at two different lengths. So this long-term planner about which roads to take is definitely a lower priority problem than am I going to hit an obstacle in 3 feet. So for example, we might want to replan less frequently in this long-term planner, figuring out what streets to take. And since I'm in a hurry, we might want to do both of these things in parallel. These are all different search problems, and so they're sort of naturally parallelizable algorithms. I will admit that I'm not a roboticist, but these people are. And in this paper, they suggest this as, minus the parallelism, as a nice design for a motion planner in this sort of hierarchical fashion. I should mention also that there's really a third process going on, which is at an even higher priority than either of these two, which is the event loop that takes input from the sensors and provides output to the motors. And that's not necessarily a parallel algorithm, but it's an interactive process. And so we have these three different processes, two that are parallel, one that's interactive, all running in the same system. And we want them all to get sort of their share of the time. We don't want to starve the low priority computation, but we also want to make sure that the high priority computation remains parallel. Now, when I say parallel, because we're all functional programmers here, I mean what I call cooperatively parallel, which is the kind of sort of implicit parallelism that we saw in the previous talk, where you specify where the opportunities for parallelism are, and then the language runtime actually decides which of those opportunities for parallelism can actually be profitably used and schedules them onto the processors that you have available. So we use high-level abstractions, and as I said, the parallelism is really managed by the runtime, as opposed to something like p-threads on the top line of this table, which is definitely not cooperative. You could certainly express this system in p-threads. It's interactive, it allows you to specify priorities as we have, and it provides for fairness. You can specify the nice values of different threads, but it's not cooperative. You would have to do a lot of this scheduling manually, this work that cooperative languages do automatically. On the other hand, the kind of prototypical cooperative language is Silk, an extension of C with cooperative parallelism, which work quite well for sort of purely computational processes, but as soon as you add interaction, it doesn't really know how to handle that. There are other languages like Go and like concurrent versions of Silk that handle interaction a little bit better, but they still don't have priorities. And so if you have say millions of computational threads, as might be generated in an implicitly parallel program, and one interactive thread, you really want to be able to specify that that one interactive thread is somehow higher priority than the millions of computation threads, otherwise the system may just never get to it. And so at ICFP last year, my co-authors and I presented a system that adds priorities to a cooperatively threaded language. But it still doesn't address this question of starvation. It just blindly applies the priorities. And so in our robot motion planning example, the low priority planner would never actually get to run because there's a higher priority planner that's always running. And so in this paper, we extend that prior system with a notion of fairness. So you can say, yes, this is higher priority than this other thing, but we still want to make sure that the lower priority task doesn't starve. So I want to motivate fairness by thinking about it instead as what we call stretch, which is how much am I okay with this computation stretching from how long it would take if it ran in isolation. So for example, the event loop is very important, and so maybe we're only okay with that running twice as slowly. It needs to run a little more slowly because there's other stuff going on in the system, but we don't want it to run too much more slowly. The medium priority short-term planner, maybe we're okay with that stretching by 3, and maybe we're okay with the lower priority computation stretching by 6. So you might wonder both where I got these numbers from, how we would actually implement this in practice, and if I just make up numbers for stretch, how do I know if this is even feasible to accomplish? So all of these questions can be answered by translating to a different notion of fairness, which we just call fairness. We formalize it with fairness criterion, which is a specification of how much of the CPU time you want to give to each of the priorities. So you can, for example, accomplish the stretch goals at the top by saying that the high priority computation should get half of the time, medium should get a third of the time, and the low should get a sixth of the time. So you'll notice two things here. One is that this looks suggestively like a probability distribution. That'll come up later. And the other is that stretch is the inverse of fairness. So if you remember one thing from this talk, stretch is the opposite of fairness, or more precisely, the inverse. This is sort of intuitively true. I've motivated it on this slide, but it's actually a theorem that we prove in the paper and that I'll demonstrate later. So I have to get there first by explaining how we model parallel programs and also how to model the scheduling of them. Then we'll prove bounds in the stretch. We also developed a more concrete algorithm for parallelizing programs, or scheduling parallel programs in this form. We have some results based on that. And then finally, because this talk is all about getting to important things quickly, I will conclude so we can all go to lunch. Traditionally, we model parallel programs as directed acyclic graphs, or DAGs, where nodes represent pieces of the computation that are sequential, and the edges represent dependencies between them. So if two things don't have an edge or a path between them, they can be run in parallel. Now, for cost tracking purposes, you want to be thinking in the back of your head as each of these nodes as a unit time measure of computation, so maybe a processor instruction. Of course, in my drawings on the slides, I'm actually not going to represent them that way because then the slide would look like this. But that should just be the model in the back of your head. So once we have a DAG, we can add priorities to the nodes by giving them different colors. So red is high priority, pink is medium priority, and white is low priority. And once we have a DAG, now we can talk about actually scheduling it. And so the traditional model of scheduling, don't ask me why, is in terms of this pebbling game. So you have a handful of pebbles, and you want to place a pebble on each of the nodes of this DAG. You can place some number of p pebbles at a time, and you can only place a pebble on a node if all of its ancestors have already had pebbles. So we can start at the top, and at the moment there's no parallelism, we just have to go in sequence. But now we can place 2 at a time, and eventually we can start placing 3 at a time. I'm going to stop here, though, and say that normally what we care about when we construct one of these schedules is the total amount of time it takes to pebble the whole graph. But I've motivated this work by talking about individual threads being starved or not starved. And so we actually want to talk about not the overall computation time of the whole program, but the individual, what we call response time of a single thread or a piece of the DAG. So maybe this piece represented by this diamond here, the nodes that are sort of bolded. And so the response time starts ticking when that piece of the DAG first appears, and it stops ticking when that last vertex is executed. So we want to bound the response time of, in particular, low priority threads to make sure that they don't get starved. So what are the sorts of things that that bound could depend on? Well, it could depend on what we call the competitor work, which is the amount of work that's in the system at the same time, so could happen in parallel with the thread that we're interested in, and at the same priority. Because we're considering the priorities separately with this fairness criterion, we're only concerned about work that's at the same priority. And so the only work that's competing with these 4 vertices we care about is this other one over here, because it could happen in parallel and it's at the same priority. We also care about the critical path, because no matter how many processors you have, you still have to execute paths in sequence. And so the longest path in this piece of the DAG that we care about is these two edges here, or equivalently these other two edges here. So those are the two things that we want our bound to be able to depend on. So how do we get a bound that only depends on those two things and takes fairness into account? Well, I talked before about pebbling, but I didn't specify any constraints on what nodes you could pebble. I didn't specify that you could only do higher priority ones before lower priority ones and so on. So now we devise a scheduling principle called the fairly prompt scheduling principle, or fair and prompt, which attempts to be fair according to the fairness criterion you specified, but also give high priority processes more CPU time whenever possible. So the way we think about this is you have your pebbles over here. Now let's paint each of the pebbles with some color according to the colors of our vertices. So let's say we want to spend twice as much time on these red vertices as on the pink ones, and twice as much time on the pink ones as the white ones. We can just color our pebbles in this way. And now we put all the pebbles in a bag and draw from the bag without looking, as up to p pebbles at a time. So in this case, up to 3. So at the beginning, there's no choice. Whatever color pebble I pick out, I still have to execute the one vertex. Now let's say we draw 2 pebbles, and we get a red one and a pink one. So the idea behind these colors is that the red pebble wants to go on a red vertex, because that corresponds to a processor that's trying to work on high priority work. And so it will, if it can. And the other pebble will just go where it has to, in this case, onto that low priority vertex. So now, in this case, we draw 3 pebbles of 3 different colors, and we have 3 vertices of 3 different colors that we can execute, so that's great. And now things get a little more complicated. So we draw 3 pink pebbles just by chance, but there's actually only 1 pink vertex. So one of the pebbles will definitely go there, regardless of what other priorities there are. And now we still have these other 2 pebbles left sitting around. So this comes to the prompt part of the principle, which is that if we can't work on the priority we were supposed to work on, let's at least get the highest priority thing in the system done. And so those 2 extra pebbles will go on these high priority vertices. So to sum up this principle, we'll work on tasks according to the fairness criterion we specified whenever possible, and if not possible, work on just the highest priority task you can. So these are the fair and prompt components. So now we're ready to specify the bound. I have a bound here, which I've suggestively left space in. This, given the definitions of competitor work and critical path that I've used on the previous slides, is the bound assuming that there are no other priorities in the system and we don't care about fairness. This bound might look familiar to you. If you were in St. Louis last year, you may have seen this young, naive, clean-shaven grad student talking about this very bound. So what's in that empty space there is precisely the stretch. It's the amount by which this computation will take longer than it would have if we had run it in isolation. And so what is that? Well, the 1 over p here means that every step we're either doing p work toward the competitor work, or we're making progress along the critical path. But when we take fairness into account, we're not doing that p work on every step. We're doing it on only steps that were allocated to this priority. So we have to multiply by 1 over the percentage of the time that we spend on this priority. And this is the inverse of fairness, which is stretch. So there's our theorem. You'll also note that we have to specify it in expectation because the definition of the scheduling principle was in terms of probabilities. But otherwise, that's it. So now I briefly want to specify the algorithm that we've actually implemented, which takes into account a couple of practical considerations not taken into account by the theory. For example, the algorithm operates in rounds of a fixed length rather than rebalancing priorities at every step, which would be impractical. Rather than use a global queue of threads that are available to run, it balances using work stealing, and it's implemented as an extension of standard ML, as opposed to the theory, which is implemented on paper. Briefly want to share a couple of results with you. So first, we claim that the algorithm is fair. So we want to measure whether it actually is fair. So what's shown on this graph on the y-axis is the expected stretch, or the actual stretch over the expected stretch. So we want to see values as close to 1.0 as possible. Everything is normalized to the computation running in isolation, which is the red bar, and the black and green bars represent different fairness criteria that we tried using. So as you can see, things remain pretty close to 1, other than for these 2 benchmarks on the right, which are more memory intensive. So there's still some work to be done here. We also want to make sure that we've been fair to lower priority processes, but we don't want to lose the responsiveness of the higher priority interactive things. So that's what we show in this next experiment. For a variety of different fairness criteria, what is the response time of an interactive process that's running at a high priority in parallel with these other lower priority computations? So you'll note that in the red fairness criterion, we only devote 5% of the cycles to the high priority computation or interaction, and response times are still pretty good. They're on the order of tens of milliseconds. And if we give even 25% of the cycles to that high priority interaction, response times get considerably better even than that. So we've not sacrificed responsiveness with fairness. This also is a theorem in the paper. There's a separate theorem bounding how much high priority threads can be hurt by fairness. There are also more details of the algorithm, and there's a comparison to Silk and to Go, which are 2 languages I mentioned in the introduction, as well as some other experiments that are detailed in the paper. So see those for details. In the future, we'd like to consider an idea of dynamic fairness criteria. So let's say that you have a process that's been running for a long time, and you're getting kind of impatient about it, and so you want to bump up the amount of CPU time that process gets. Right now, our implementation supports this, but it's not clear how to add that into the theory. So that would be one thing that would be interesting to explore in the future. And also, I said that we made a couple of changes in the algorithm from the theory for practical considerations. So the bounds that we have in theory don't necessarily apply to the algorithm, and we'd love to actually prove that those bounds are at least approximated by the algorithm in practice. So thank you.
So starting off with a question from Slido. You bound the expected response time. What about the worst case?
So we don't bound the worst case, but you should be able to use some properties of expected values, I think, to get inequalities on the worst case from the distribution and from the expected value. So I didn't do all the statistics on that, but I think it should be possible to get a bound on that as well.
Questions from the floor? Okay, we'll take the next one from Slido. Why is fairness specified only in terms of the threads at the same priority? Intuitively, one would expect fairness compared to all processes weighted.
Right, so you could specify fairness at the level of threads rather than the level of priorities. This really doesn't lose any generality because I've only shown examples with 3 priorities, but in our system we actually allow any number of priorities. And so if you want 2 priorities to have their, 2 tasks to have their fairness criteria specified separately, you could just divide those into 2 separate priorities. The coarser granularity doing it at the level of priorities is a little bit more convenient for us for practical reasons, but it doesn't really lose you any generality.
Any other questions from the floor?
So you're working with one resource, which is the CPU. We know that there are a lot of resources that are limited. Have you made any ideas of how to combine this so that you have multiple resources that are where the processes have different priorities for each different resource, considering memory, network, I/O, stuff like that?
Yeah, so that would be something really interesting to look at. So we've so far only looked at time, CPU time, and so if and even that is an interesting problem in itself that hasn't really been looked at, because even as far as time, different processes have different requirements. So the computational processes are bound more by the total length of time that the computation takes, whereas the interactive processes care much more about the response time, so between an input and an output. So there are even different requirements as far as time. And so we focus most of our effort on combining threads with different timing requirements in the same system. So it would even add another interesting dimension to that to consider, well, this thread only cares about time, this thread cares about having more of the memory, and so we want to assign those resources in different ways. So that would definitely be a cool extension to this. Thanks.
A question from Slido. How do you go about deciding which steps get which priority?
In the theory, the priority of each processor, the priority that's working at is drawn from the...
Let me rephrase the question. What is the heuristic for deciding what stretch you should apply to each?
Oh, I see. OK. The heuristic for deciding a stretch you should apply to each priority.
Yes.
It depends on the application. Sometimes there's some tuning involved. So for example, in the motion planning example, we had this derived from the robotics paper that we were looking at, the idea that one of the planners should run about 4 times as often as the other. So that sort of gives you stretch values right there. In other applications, it's not as clear what an acceptable stretch would be. And so that may be something that you'd have to tune and play around with different values. Haven't necessarily looked into better heuristics for that.
OK. Questions from the floor?
So is scheduling NP complete in terms of difficulty?
Yeah.
So the question was...
is scheduling NP complete? It is NP hard, finding the optimal schedule for a given DAG.
So how do you balance looking for the right answer in the context of uncertainty? Because obviously resources are uncertain and also getting stuff done.
Right. So finding the optimal schedule is NP hard. But there are all of these scheduling results. So the most famous one of these is Brent's theorem, which says that if you are just greedy, so in the absence of priorities, if you just are always using as many processes as you can up to the number of threads that you're able to run, you're within a factor of 2 of optimal. And so for our fairly prompt scheduling principle, we've shown a similar approximation, that you're not getting the optimal bound because that's NP hard, but you are getting within an approximation of it. And the same thing, these work stealing algorithms guarantee constant factor approximation of optimal, because getting the optimal response time or computation time is computationally very difficult.
OK, that's all the time we have for questions. So let's thank our speaker. Did they ever get this signature from you?
Yeah.
OK.